Welcome to the video on functions. Today we're going to be determining whether or not relations are functions, and then we're also going to practice evaluating functions. I've got 10 graphs here. We want to determine whether they're functions, and we use what's called the vertical line test. And the vertical line test says that if all vertical lines pass through no more than one point, then the relation graphed is a function. So this one is a yes because all the vertical lines pass through only one point. Looking at the graph below, it almost appears as though that line passes through two spots, but if we look closely, both of those are open circles. So the function does not exist at those locations, and therefore this is a function. This relation is a function. So we're going to take a look at these. Here we go. Here's our first instance of a failure. This vertical line passes through two locations, and so this is not x equals 1 has two values. So I'm specifying where I see the vertical line test failing. This graph I go through and I look for anything. I've got closed, open, so all of my vertical lines pass through and we're good. On the next pair, a vertical line right through here passes through an infinite number of values all along that line, so this one is not a function. Not a function. Okay. At x equals 1, 2, 3, there are many outputs. This graph is good. Every single vertical line passes through only one spot. So this is a yes. Then we go to this graph. This is a crazy looking graph with lots going on. At first you'd think this would be a failure, but we've got open there and closed at that dot. I know it's kind of small and hard to see. As we continue along, the vertical asymptote is fine, but right here we have closed circle above closed circle. So this one is not a function either. You could say the vertical line test fails at x equals 1 because the vertical line passes through more than one location. This one is not a function, and there's lots of spots the vertical line test fails. We'll just pick one right here. We could say the vertical line test fails at x equals 2 because we've got multiple locations that the vertical line passes through. And the last pair, we're good. This is closed at the top and open at the bottom, so that vertical line is good. So this one is yes, and this one also passes yes. So that's determining whether a graph of a relation is a function. Now we're going to take a look at mapping diagrams to determine whether these are functions. And it's fairly simple with the arrows pointing. What we want to check to see, does any number map to more than one location? So 10 only maps once, 20 only maps once, 30 maps once, and 40 maps once. So we're good. When we look at the second one, this is not a function because 2 maps to 20 and 40. So that's not a function because one of our inputs maps to two different outputs. Our third diagram is not a function because 3 maps to 4 and to -3. Our third one's not a function because 1 maps twice. 1 maps to -1 and to 0. So that 1 goes to 2 locations. Now our last diagram, this one, it depends on which direction our mapping goes, and since there's no arrows, we can assume that it is mapping in that direction, which is pretty much the norm for mapping diagrams. And in this case, each one of our inputs maps to only one output. So we will say, yes, this is a function. If we were heading in the other direction and this was our input and we were mapping that direction, then we would see a failure because 2 maps to multiple locations. So as long as the direction is left to right, then our mapping diagram is a function. Okay, looking at tables. This is very much like a mapping diagram. You can almost consider this kind of your input and your output, and you could say 1 maps to 8, 2 maps to 7, 3 maps to 9, like that. And we're good. A tricky thing that might happen on a table is you would see a duplicate x value saying that the number 1 maps to 2 different locations. 1 maps to 8 and 1 maps to 7. So this is not a function. 1 maps to 8 and to 7. Okay. And as long as our direction is from the left column to the right column, like that, then we're good. But we see here again the number 2 is mapping to both 7 and 9, so this is not a function. The next one, you see all of these repeat 8 values, but 1 maps to 8, 2 maps to 8, 4 maps to 8, 10 maps to 8, and 18 maps to 8. This is a fine setup. It is allowed. You can have multiple inputs mapped to the same output. What you don't want to have is one input mapped to 2 different outputs. Another thing that we'll see in a table is sometimes there's an input that doesn't map anywhere, and that's fine. That doesn't make it not a function, so long as none of our inputs map to more than one output. So we don't see any repeats on the inputs, so we're good. This is a function. And then finally, looking at equations to determine whether or not expressions or equations are functions, what you want to do is ask the question, can you solve this for the variable? So if I were to solve this for y, I would get 5 minus 2x over 3. And that is a single equation with an input of x and an output of y. So yes, it is a function. Of x, so our input x would produce the value y. Looking at the second equation, if we were to solve this for y, again, this is solvable for y, and we get 10 minus x squared divided by 5. We were able to solve it for a single y value, so yes, it is a function. The third one, if we tried to solve this for y, what we get is y is the positive and negative square root of 25 minus x to the 4th. And because when we took the square root, we had to introduce the absolute value and thus the positive and negative. What this is one input can yield 2 different outputs, and so this is not a function. Not a function. All right, let's look at the second part of the notes, and this is evaluating functions. Here we're going to evaluate functions first from an equation, And I've got 3 examples here. F of -1 means we plug -1 into the equation, and we get 1 plus 5 is equal to 6. F of 4 means plug 4 in for all of the x's, and we get 4 squared minus 5 times 4. That's 16 minus 20, which is -4. I can even evaluate the function at another variable. So this says plug a in for all of the x's, and I get a squared minus 5a. That's not a terribly complex equation. It doesn't really need to be simplified at all. If I plug a plus h in, what I'm going to get is a plus h squared minus 5 times a plus h. And that may be the cleanest this expression can look. For the purpose of evaluating functions, we're good there. We have done the process. But it might be possible to expand this by foiling the first term and distributing, and then seeing if things cancel out. I'm not going to do that, but we will later on in the year. Okay. 12 over x minus 5. If I stick 11 into that, I get 12 over 11 minus 5, which simplifies to a value of 2. If I stick 5 into the expression, I get 12 over 5 minus 5, which puts 0 in the denominator, and that's not possible. So the answer does not exist. If I evaluate g of a, that would be 12 over a minus 5. And if I do g of a plus h, that's 12 over a plus h minus 5. As you can see, all we're doing is we're taking what's in the parentheses here and replacing it with the variable. Okay. One last example. This one's trigonometry, and if you've learned trigonometry, that's great. If you have not yet, well, plug pi 6 in and we're still able to do it. The student who has learned trigonometry would know that sine of pi 6 is equal to 1/2. If we want to evaluate it at 3 pi halves, we would say sine of 3 pi halves. And the student who has learned trigonometry knows that that value is -1. Evaluating v of a, we're going to plug a in for the variables, and we'll get sine a. Or if we want to evaluate it a plus h, we plug a plus h in there, and we get sine of a plus h. And neither of those can be simplified further. Okay, that's evaluating from a equation for the function. Now we'll evaluate from mapping diagrams and tables. These are very quick. h of 20, 20 maps to 45. h of 35, well, 35 is not defined in our input, so we could say not defined. Some people might say does not exist, or no solution. I like not defined because it is not defined for 35. g of 2, we find our 2, we see that 2 maps to -2 if we assume the mapping direction is this way. g of -1 maps to +2. Okay. Evaluating a function from a table, f of 15 produces an output of 25, and f of 25 produces an output of 5. Easy enough. And then evaluating from a graph. f of -4 means go to where x is -4 and find where the function exists. The function exists at -4, 4. So f of -4 is 4. That's that location right there. If I want to evaluate f of negative 2, I'll go to negative 2, and I see that the y-coordinate at that location is positive 2. F of negative 1 is also a value of 2. So when we go to negative 1, the height is this closed circle, not the open circle. F of 0 is negative 1. That's that location right there. And f of 3, 1, 2, 3, does not exist because there is an open circle at that location. Okay. A second graph, this time we're evaluating g of x. G of negative 2 is a height of 3. G of 3, 1, 2, 3. G of 3, there is a vertical asymptote there, so G of 3 does not exist. G of 4, that's where the curve is, right there at 4, comma, negative 1. So G of 4 is negative 1. G of negative 4, G of negative 4 is negative 1. And G of 4.5, this is where the graph is not exactly precise, but if we go to 4.5, we can see that we are slightly smaller than negative 1, so I'm going to approximate this. So I'll change this into an approximately equal to negative 1.25. So there we have it, evaluating functions. Thanks for watching this video. Be sure to comment, like, and subscribe. Have a good day. Bye-bye.